All right, so in this video, we're going to be going over sections 1.5 and 1.6 from our textbook. So we'll start off with 1.5, which is about exponential functions, and these are used widely for modeling and solving a variety of real-world problems like population growth, radioactive decay, and more. And we'll see that in this chapter as well. But we'll start with the definition of an exponential function. And that is this here. The equation f of x is equal to b to the power x for b greater than 0 and not equal to 1 defines an exponential function for each different constant b, which is called the base. Now the domain of f is the set of all real numbers, and the range is going to be the set of all positive real numbers. Now just something to note here that this equation f of x is equal to x squared is a quadratic function, and g of x is the g of x here, which is equal to 2 to the power x, is an exponential function. So these are different, and that's something to keep in mind when we're looking at these. Now, theorem 1 here describes the basic properties of the graph of our exponential function here that is of this form. And you can kind of read through these and check for yourself, but we'll see that this is the case for each graph of f of x. And then theorem 2 has some properties of exponential functions, which we can also read through. These are our exponent laws, which we should all be pretty comfortable with. We have the fact here that a to the power x is equal to a to the power y if and only if x is equal to y. So this is important to note and will help us when solving log functions. And then we know that for x not equal to 0, a to the x equals b to the x if and only if a is equal to b. So these are all properties we should be fairly comfortable with. All right, so let's talk about our base e exponential function. So this is our most commonly used base. It's because in certain formulas and certain results that we'll see in advanced mathematics classes, take on their simplest form if the base e is used, and then e is equal to this number here. Okay, so the exponential functions with base e and base 1 over e are defined by y is equal to e to the power x and y is equal to e to the power negative x. And here is our domain and range here. So here are the graphs of e to the negative x and e to the x. And you kind of see their behavior here. All right, so we're going to talk about growth and decay applications. So we're going to be looking at functions of this form here. Y is equal to c times e to the power k times t. And c and k are going to be constants. And our independent variable t is going to represent our time. And this is often used to model population growth and radioactive decay. And something to note here is that if t is equal to 0, then y is equal to c, right? Because e to the power 0 will just be 1. So our constant c here represents the initial population, so the initial amount that we're looking at. And our constant k here is called the relative growth rate and has a few properties. Let's suppose that we have this y is equal to c times e to the power kt, and that'll model the population of a country where y is the number of persons and t is the time in years. If that's the case, and if the relative growth rate k is equal to 0.02, then at any time t, the population is growing at this rate, which ends up being 2% of the population, and this is growing per year. So in this case, we say that the population is growing continuously at a relative growth rate k. All right, so what we're going to do to kind of better understand this is look at an example. So we're told that cholera is caused by a cholera bacterium that multiplies exponentially, and the number of bacteria grows continuously. So it grows continuously at a relative growth rate, 1.386, and we have this equation here. Now, N is going to be the number of bacteria present after a certain amount of time, and then N naught here is the number of bacteria present at the start, so our initial amount. And this N sub 0 here is pronounced N naught, and whenever we see a number with this 0 here, that's always going to indicate and let us know that that is going to be our initial amount. Okay, so we are going to start with 25 bacteria, and we want to figure out how many bacteria will be present at 0.6 hours and in 3.5 hours. Okay, so this might seem a little intimidating at first, but this equation is just how we set up here. We have our model, and that is y is equal to c times e to the kt. And in this case, with this equation that we're given here, we just have that n is equal to y, and our n naught is equal to c. So we're just doing the same thing, we just have different variables, but our model is the same. Now, what we're trying to do is find this value in here, so the number of bacteria present after t hours. And in part A, our t is going to be 0.6 hours. And we have all of our information needed, actually. We can plug into our equation. So N naught, remember, is our initial amount, and we're told that we're starting with 25 bacteria. So N naught, plugging that in there, is 25. Then we have e to the power k times t, and we're told that k, which is our relative growth rate, is 1.386. And we want to figure out n after 0.6 hours, so we plug that in for t here. All right, and then plugging this into a calculator, we end up with 57 bacteria. All right, so that is the number of bacteria present after 0.6 hours. And in part B, we're going to do the same exact thing. The only thing that changes here is our value for t. So plugging everything into our equation, and using a calculator, we get 3,197 bacteria. All right, so that was an example of exponential growth. And what we'll look at next is an example of exponential decay. All right, so there's a lot here. Okay, so we're told that the cosmic ray bombardment of the atmosphere produces neurons, which in turn react with nitrogen and produce radioactive carbon-14. Now, this radioactive carbon-14 enters all living tissues through carbon dioxide, which is first absorbed by plants. And as long as the plant or animal is alive, the carbon-14 is maintained in the living organism at a constant level. However, once an organism dies, the carbon-14 decays according to this equation here. And since, a side note, since we are working with exponential decay, this means that k, our rate here, is negative. So instead of it being our growth rate, it's our decay rate. Okay. A is going to be the amount present after 2 years, just like we saw in the previous example. this here is pronounced A naught, and it is the amount present at time t equals 0, or the initial amount that we're starting with. And we're told that if 500 milligrams of our carbon-14 is present in a sample, how many milligrams will be present in the sample in 15,000 years? So we're starting off with A naught is going to be equal to 500 milligrams. We're given that our time in years is 15,000 years. And we already know what our relative decay rate will be. So we can just plug all of this into our equation. We're looking for A, the amount present after 15,000 years. So plugging in our A naught, and then our K is this here, and then T is 15,000. And again, using a calculator, we get this is equal to 77.84 milligrams. All right, and that is an example of exponential decay. Now what we're going to look at is compounding interest. So the fee paid to use another's money is called interest, and it is usually computed as a percent, which is called the interest rate, and it's a percent of the principal over a given amount of time. And if at the end of a payment period, the interest due is reinvested at the same rate, then the interest earned as well as the principal will earn interest during the next payment period. And so the interest paid, on interest reinvested is called our compound interest, and it can be calculated using the following formula. So we let capital P be our principal or present value, and it will be invested at an annual rate, which will be R, and that is expressed as a decimal. And if it's compounded a certain amount of times per year, represented by M, then the amount A will be our future value in the account after a certain amount of years, is given by this formula here. So this is our compound interest formula. And what we're going to do is look at an example of how we can use this. So let's say that we're told that $1,000 is invested in an account paying 10% compounded monthly. And we want to figure out how much will be in the account at the end of 10 years. So all we have to do is use this formula here for our compounding interest. So we know that A will be our future amount, so this is what we're trying to find. So we're not sure what that is, that's what we're trying to find. We know that our principal is our initial amount, so that was $1,000. We know that R is going to be our interest rate, so that's 10%. And then remember, we're writing this as a decimal, so this will actually be written as 0.1. And then we know that this is being compounded monthly, so M is going to be 12 because there's 12 months in 1 year. And we want to figure out how much will be in the account after 10 years, so T is equal to 10. So plugging this into our formula above, plugging everything in, and then we plug this into our calculator, and we get, there will be $2,707.24 in our account at the end of 10 years. Now, if a principal P is invested at an annual rate R, but it's compounded continuously, then this changes our formula a little bit. We actually end up with this guy here, and this is our continuous compounding interest formula. And remember, our constant e is the base of the exponential function here. So if we were given pretty much the same parameters as the previous example, but we're told that we're working with continuous compounded interest, we want to figure out how much will be in the account at the end of 10 years. So what we'll do is we'll use our continuous compound interest formula and plug in what we know. Again, we're starting with $1,000. That's our principal, so that's P here. Then we have our base E, and then our rate is still 10%, and written as a decimal, that's 0.1. And then we want to figure out how much will be in the account at the end of 10 years. So plugging this in, we end up with $2,718.28 at the end of 10 years. All right, and that is continuous compounding interest. And here is a little summary here. You can find this in the book as well. Here's our formula for compound interest and continuous compounding interest. And here is a list of our parameters. All right, now that was section 1.5. And now we're going to talk about section 1.6, which is about logarithmic functions. So we'll start off by looking at the definition of a one-to-one function. So a function f is said to be one-to-one if each range value corresponds to exactly one domain value. Now here are two examples. First, we look at our function f of x is equal to 3x. And so as you can see, this function is one-to-one. It is each range value, so all of the values here correspond to exactly one domain value. So these are the result of only one input here. Whereas if we were to look at this function, x squared here, this is not one-to-one. And this is because the range values 4 here and 1 both correspond to or are the result of two different inputs. So 4 is the result of -2 and 2, and then 1 is the result of -1 and 1. So this tells us that this function is not one-to-one. All right, so now we want to look at the definition of an inverse function. So if f is a one-to-one function, then the inverse of f is the function formed by interchanging the independent and dependent variables for our function f. This means if AB is a point on the graph of f, then BA is the point on the graph of the inverse of f. And then the reason we even brought up one-to-one functions is because if f is not one-to-one, then we automatically know that f does not have an inverse. So if we start with the exponential function f defined by y is equal to 2 to the power x, and we interchange our x and y variables, then we obtain the inverse of f, which is x is equal to 2 to the power y. Now, we call the inverse the logarithmic function with base 2, and we write it as y is equal to the log function with base 2 of x if and only if x is equal to 2 to the power y. Now this brings us to our definition of a log function, and it's that the inverse of an exponential function is called a logarithmic function for b greater than 0 and not equal to 1. We have the log form here, and it's equivalent to our exponential form here. Now going back up to this example here, since our log functions is the inverse of our exponential function, what we can do is we can write these interchangeably by using that property. So for example, this here, y is equal to log base 2 of x. If we were to take base 2 on both sides, since these are inverses, we end up with 2 to the power y is equal to x here. And we can do the same thing on this side with x is equal to 2 to the power y. We can take log base 2 on both sides. And again, exponential and log functions are inverses. So we end up with, log base 2 of x is equal to y. So we can use this fact, the fact that an inverse of an exponential function is a log function, to find the following. So we'll look at a few examples here. First, looking at A, we have y is equal to log base 9 of 27. So what we want to do is find y. So we'll take base 9 on both sides, since these are going to be inverses, and we get 9 to the power y is equal to 27. Now this is where we need it to be a little bit clever with how we're trying to find y. And we'll do this by rewriting 9 and 27 so that they have the same basis. And we'll start by saying we know that 9 is equal to 3 squared. And then on the right hand side, we know that 27 is equal to 3 cubed. And then using our exponent rules, we end up with 3 to the power 2y, and that's going to be equal to 3 cubed. Now, something to note here, it must be the case, let's actually write this down. It must be the case that 2y is equal to 3 here. Since we have 3 to the 2y power is equal to 3 to the cubed, the exponents must be equal, since we're saying that these guys are equal. And I don't know if you remember in the beginning of section 1.5, there was a property, an exponential property that told us this, and I said that this would be important for solving log functions. So if you don't remember that, scroll back to section 1.5. But since we have just scroll to section 1.5. Okay, so then this tells us that 2y is equal to 3, and then we can easily solve for y, and that'll be equal to 3 over 2. Alright, so not too bad. Let's look at example B. We want to find x when we're given log base 3 of x is equal to -1. So again, we're going to use our inverse property. Take this to base 3, and we end up with x is equal to 3 to the power -1, and then our exponent rules tell us that this is the same as 1/3. Alright, so pretty simple. Let's look at our last example, C. This is, sorry. This is log base b of 1000 is equal to 3, and we want to find b. So we'll take base b on both sides, and then we end up with 1000 is equal to b cubed. And then now what we can do is take the cube root on both sides to solve for b, and this ends up being 10. Because 10 cubed is 1000. Alright, so pretty simple there. Now let's talk about some properties of log functions. Now these are going to be very important when solving for, or just working with log functions in general. So be sure to look these over, and what we'll do is we'll look at a few examples in order to illustrate these properties. So let's look at this example here. We're given this big equation here, and we want to find x. So I'm going to start with rewriting this here in terms of some of the properties that we see up here. The first being that we have this 3 times log base b of 2. And if you look at property, sorry, I just had it. Oh, property 7 here. It says that if we have log base b of some number m to some power p, that's the same as multiplying our log base b of m times that power p. So we're essentially just bringing this power in front. And so I will rewrite this guy using that property. So we have log base b of 2 to the power 3. All right. Now I'm going to do the same pretty much with each term here. Let's look at this one. We have log base b of 25 times 1/2. And using this same property with this exponent, we can bring that back here. So that ends up being log base b of 25 to the 1/2 power. And then log base b of 20, we don't really need to change anything there. And this is going to be equal to log base b of x. Remember, we're trying to find x. All right, so let's do a little bit of simplifying. We know that 2 cubed is 8, so this ends up being log base b of 8. And we know that 25 to the 1/2 power is the same as 25, or the square root of 25. So I'll just write that here. And we know that the square root of 25 is 5. So we can rewrite that like that. And then our log base b of 20 and log base b of x stay the same. All right, now the next property we're going to use is with these guys here. And scrolling back up, that's going to be property 5. And so this tells us that the sum of two log functions with the same base is the same as taking the log of the product of the two numbers. That's a little bit of a mouthful, but what we can do is rewrite the sum of these guys just like this here. And so we end up with, write this in blue, log base b of 40, because we're just multiplying 8 and 5 here. And then we still have our log base b of 20, and all of this is equal to log base b of x. All right, now the next property we're going to look at is with these guys here, and that is this difference property, property 6 here, which says that if we are taking the difference of these two log functions, that's the same as taking the log of this quotient here. So we'll rewrite, let's do green, we'll rewrite this as log base b of 40 over 20, and then this is equal to log base b of x. All right. Then 40 over 20 reduces to 2. So we have log base b of 2 on the left-hand side, and that's going to be equal to log base b of x on the right-hand side. And property 8 here tells us that log base b of some number m is equal to log base b of some number n if and only if m and n are equal to each other. So this property tells us that 2 must be equal to x. All right, and that is how we use these properties to solve log equations. All right. So of all the possible log bases, base e and base 10 are used the most, and our terminology for those is our common logarithm means log base 10, and then our natural log will be log base e. All right, so we'll look at a few examples. So we have log base 10 of x is equal to y is the same thing as writing x is equal to 10 to the power y. And same for natural log base e of x is equal to y is the same thing as x is equal to e to the power y. So again, just using the fact that our exponential and log functions are inverses. And we'll look at a few examples of this. So again, our log and exponential functions are inverses. So looking at example A, we can just take log base 10 on both sides. So we end up with this canceling. We get 10 is equal to log base 10 of 7. And so when we're omitting it like that, we're automatically assuming that this is base 10 here. And then using a calculator, we get that x is equal to 0.8451. And there we go. Doing the same thing for example B, we have our base e here, so we're going to use our natural log on both sides. So these cancel, and we end up with x is equal to natural log base e, we don't have to write that, of 6. And so then x is equal to 1.7917, and then we're just using a calculator for that as well. And lastly, we'll do the same thing for example C. We're doing log base 10 on both sides here. So we end up with x is equal to log base 10 of 5. And this tells us that x is equal to 1.1609. Alright, so that's how we'd solve for x when dealing with log base 10 and our natural log here. Now the last thing that we'll look at is an application. So a convenient and easily understood way of comparing different investments is to use their doubling times. So pretty much the length of time it takes the value of an investment to double. And as we'll see in the next example, log properties provide us with just the right tool to solve these doubling time problems. And something to note here is that problem 10 in the textbook, or example 10 as it mentions, does talk about doubling time. But I wanted to do the matched problem 10. You'll see in the textbook that they'll give an example and then a matched problem for you to kind of do on your own. But I wanted to do that one so we could see another example because there's no solution for that in the text. And in this example, we're actually looking at how long it'll take something to triple. So let's start at the beginning. Let's read this problem. It asks, how long will it take money to triple if it is invested at 13% and it's compounded annually? So this here is given to us, and this is our formula for compound interest. And what we want is to find t, because it asks how long will it take for this money to triple. So t, we're not sure what that is, that's what we're looking for. But we are given our rate, and that is 13%, written as a decimal, that is 0.13. We're also told that it is compounded annually, so only once a year, so m is equal to 1. And we want to figure out how long it'll take our money to triple. And remember, P is our initial amount that we started with. So this means what we end up with, which is A, is going to be 3 times the amount that we started with. Alright, so plugging this into our equation, we know that A is equal to 3P, and we have 1 plus R, which is 0.13, over M, which is just 1, to the power M times T, and M is just 1, so that's just 1 times T, which is T at the top there. Alright, since we have P on both sides, these cancel, so we'll end up with 3 is equal to, and we just have 1 plus 0.13, since 0.3 divided by 1 is still just 0.13. So we end up with 1.13 to the power t. Now, what we can do is take the log of both sides, and we end up with log of 3 is equal to log of 1.13 to the power t. Remember, with our with our logarithmic properties, we can rewrite our function when it has an exponent like that, like this. So we can rewrite this as t times log of 1.13. And then all we have to do is solve for t. So we'll divide by log of 1.13 on both sides here. So then t is equal to log of 3 divided by log of 1.13. All right, and this is our answer. Sorry, I did not put that in the calculator in advance, so I don't know the exact number, but you're welcome to plug it into a calculator. And that is how long it would take our money to triple if invested at 3% and compounded annually. All right, so that is sections 1.5 and 1.6 in the textbook. Thank you.